Day 518 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 407, Trapping Rainwater 2. The difficulty level is hard, but don't worry because you already know we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, hype, subscribe, comment, and share. And if you need any new Apple AirPods, go in and check out that link in the description so you can get you some. Now let's see what the question says. Given an m by n integer matrix height map representing the height of each unit cell in a 2D elevation map, return the volume of water it can trap after raining. All right, y'all, so that may seem a little bit confusing at first. Let's go ahead and take a look at these examples just to make sure that we are doing this problem correctly. So in example 1, we have our input height map is a 2D array of integers, first array being 1, 4, 3, 1, 3, 2, then 3, 2, 1, 3, 2, 4, then 2, 3, 3, 2, 3, 1. The output is 4. Explanation says, after the rainwater is trapped between the blocks, we have two small ponds, 1 and 3 units trapped. The total volume of water trapped is 4. All right, y'all. So that may seem a little bit confusing at first. So let's take a look at this nice diagram or picture that they give us so we can make it make sense and even further. So first we want to understand that each row in these group of blocks represents a different array, right? So this array this row right here that we can see, this first row we can see, this is represented by this array right here, right? As you can see, first it has 2 blocks, then it has 3 blocks, then it has 3 blocks, then it has 2 blocks, then 3 blocks, then 1 block. And this goes 2, 3, 3, 2, 3, 1. So this array represents how many blocks are in this first row. Then this array represents how many blocks are in this middle row, right? So as you can see, we have 3 right here. So that's why there's an extra block right here. Then it's 2, 2, which allowed us to fill up the ponds. Then, 2, 1, and then we have 3, 2, and 4. And finally, this last row behind that we can't see is represented by this row, 1, 4, 3, 1, 3, and 2. Now, we want to see how much rainwater will get trapped after it rains. So as you can see, we have these 3 blocks right here, right? Boom, boom. That's forming some type of border or wall that's going to trap the rainwater, and it's represented right here by these 2 3s. Then, as you can see, the corresponding index in the row, this row right here, or this array, this has 4, and this has 3. So these line up, and this has an extra one. But you can see it's a dip right here because this has 2 and 1. So that means there's only 2 blocks right here that we can't see, but there's 1 block of rainwater, and then there's only 1 block right here that we can't see, which allows 2 blocks of rainwater. So that's the gist of what we're trying to solve. Similarly, right here, we have 3 right here, then we have 3 right here, and we have 3 right here, and we have 2 right here. So that means that there is 1 block of water right here that we can add, and in total is these 3 blocks of water plus this 1 block of water gives us a total of 4 units of water that were trapped during the rain. So just in case that didn't make sense, let's take a look at example 2. Example 2, it seems a little bit simpler, but is it really? Let's go through it and check to make sure. So in example 2, we have our input height map equals a 2D array of integers, 3, 3, 3, 3, 3. Next array, 3, 2, 2, 2, 3. Then the array after that is 3, 2, 1, 2, 3, then 3, 2, 2, 2, 3, then 3, 3, 3, 3, 3. Now, same principles apply. So this is going to be, this right here is going to be this first row right here. Then this right here will be this second row right here. Then this array right here will be this third row. Then this will be this 4th row, and then finally this will be this 5th row right here. Now, as you can see, the first row right here and the last row the first row right here and the last row right here are all equal. They all have the same height, same rows. So that lets us know that the water is going to be trapped in between these rows right here. Similarly, if we were to do a grid, then we'd be able to see that this row right here, so this second row, it starts at 3, or excuse me, right here, starts at 3 and ends at 3. That's why it's at 3 blocks right here and 3 blocks over here. However, in the middle, there's only 2. So these only come up to 2, which means we have an extra unit of water right here, 1, 2, and 3. So that's 3 extra units of water right here. Then similarly in this row right here has 3 blocks over here and 3 blocks over here. But here it only has 2, so that's 1 block of water. Then here it only has 1, so that's 2 blocks of water. Then right now we're at a total of 3 blocks of water. Then right here it's a 2, so that gives us another block of water. So in total that's 4 blocks of water. So first we have so now we're at 3 plus 4. Boom. Then we check this row right here. This row, once again, this is 3, this is 3. All these in the middle are 2, which means we have 3 blocks of water right here, 1 on each cell. So then that'd be plus 3. And then 3 plus 4 plus 3 equals 10. And thus, our output would be 10. So I hope that makes sense to y'all. And now that we understand the question, let's get into the fun part, the actual solution. Solution's not that difficult. It's a little lengthy, but we should be able to get through it. So let's get to it. Now, first thing we want to do is we want to get the dimensions of the grid. So we're going to say let M equal height map. Height map dot count. Boom. Then we're going to say let N equal height map square bracket 0, come outside the square brackets, then say dot count. Boom. Then we want to track the visited cells so we don't process them twice. So we're going to declare a variable called visited. It's going to be a 2D array. So we're going to say equals array. Open up the parentheses. It's going to be repeating colon another array because it's a 2D array. And then that second array is going to be repeating colon false. So it's going to be repeating a Boolean of false, count colon up to n times. Then we're going to come outside of those parentheses, still inside the other parentheses, and we're going to say count colon m. Boom. Then there's going to be 4 possible directions, right, down, left, and up. So we need to say let SDV equal, open up the square brackets, open up the parentheses. We're going to say 0, 1, come outside those parentheses. We're going to say comma. Then we're going to open up some more parentheses, say 1, 0, come outside those parentheses, say comma. Open up some more parentheses, 0, -1. Come outside those parentheses, comma, and then we're going to say, open up some more parentheses, say -1, 0. Boom. Now we need a min heap simulation, which is just an array where we pick the min manually, and this is going to store tuples of height x and y. So we're going to come underneath this, and we are going to declare a variable called heap and set that equal to an array. Open up the parentheses. We're going to say height colon int, comma x colon int, comma y colon int. Boom, initialize it with 2 parentheses outside the square brackets like that. And then we need a variable to store our final answer or the total water that has been trapped. So we can declare a variable called ans and set that equal to 0. Boom. Now we need to add all boundary cells to the heap, and these act as the walls from where the water can be trapped inward. So we're going to say for I in 0 ... less than m. We're going to open up the brackets, and we're going to say for j in 0 ... less than n. We're going to open up the brackets, and we're going to say if I equals 0 or two vertical lines, j equals 0, or two vertical lines, I equals m minus 1, or, so two more vertical lines, j equals n minus 1. Then we're going to open up the brackets, and we're going to say heap dot append, open up the parentheses, open up some more parentheses, and we're going to say height map, square bracket I, come outside that square bracket j. Then we'll come outside that square bracket, we're going to say comma, outside the square bracket, still inside the parentheses. Sorry, y'all, I don't know what's going on. There it is. Outside the square bracket, still inside the parentheses, we're going to say comma I, comma j. Boom. Then we can come underneath this and we can say visited, square bracket I, square bracket j, set that equal to true. Boom. Now we need to process the cells starting from the lowest boundary. So to do that, we're going to come right here underneath this for loop, and we are going to say, we're going to come right here, and we are going to say, while exclamation point heap dot is empty, which means while heap is not empty, that's what that exclamation point means. We're going to open up the brackets, and we're going to find the cell with the smallest height in the heap. So it's going to be a big O of n scan instead of true priority queue. So we're going to declare a variable, and we're going to call it end. We can say end underscore min. Set that equal to 0, comma, min underscore h. We're going to set that equal to heap dot first exclamation point dot height. Boom. Then we come underneath this variable. We're going to start another for loop. We're going to say for I in 0 dot less than heap dot count. We're going to open up the brackets, and we're going to say if heap square bracket I dot height is greater than, or excuse me, is less than min square bracket h. Then we're going to open up the brackets, and we're going to say n underscore min equals I, and we're going to come underneath that and we'll say min underscore h equals heap square bracket I, come outside the square bracket dot height. Boom. Then we come right here, and we are going to say, I'll come right here underneath the for loop, and we are going to remove this cell from the heap to process it. So we're going to say let, open up the parentheses, height, comma x, comma y. We're going to set that equal to, so equal heap dot remove, open up the parentheses, at colon end underscore min. Boom. Then we come underneath that, and we need to explore its neighbors, and we're going to do that by coming underneath here. We're going to say for, open up the parentheses, dx comma dy, n, come outside the parentheses, n sdv. We're going to open up the brackets. We're going to say let nx equal x plus dx. Boom. Then we're going to say let ny equal y plus dy. Boom. And if a neighbor is inside the grid and not not visited, we could check that by saying if nx is greater than or equal to 0, and two and signs, nx is less than m, and two more and signs, ny is greater than or equal to 0, and two more and signs, ny is less than n, and two more and signs, exclamation point, visited, square bracket nx, square bracket ny, Come outside of that, we can open up the brackets. And water can be trapped if the neighbor is lower than the current height. The new effective height is the max between neighbor's wall and the current boundary. So we're going to say let new height equal max, open up the parentheses, height, comma, height map, square bracket, and x, square bracket, and y. Boom. And if a neighbor is lower, we're going to trap the water. If the neighbor is lower, then trap water is going to be equal to the difference. So we come underneath this, we're going to say ands plus equals max, open up the parentheses, 0, comma, height minus height map, square bracket, and x, square bracket, and y. Boom, and then we push the neighbor into the heap for further processing by coming underneath this, and we say heap dot append, open up the parentheses, open up some more parentheses, pass in new height, comma, nx, comma, ny. Boom, then we can mark as visited by coming right here, and we're gonna say visited, square bracket, nx, square bracket, ny, set that equal to true. Boom. Sorry, y'all. True. Just like that. And then finally, all we need to do is return the total water that has been trapped by coming right here. And we're going to say return ands. Boom, y'all. That should be all she wrote. Let's give it a run. Make sure it runs properly. Okay, we have an error. Let's see what should be a dot right here after this exclamation point. So let's go ahead and run that again. Okay. Let's see, y'all. Give me a moment. Hold on. Well, first let's fix this. See what that does, that typo. See, we get rid of that. Okay, expected after if. Doesn't need a space. I don't think that's it though, y'all. That's not it. Oh, here it is. Boom. Put that space right there. Now let's run it. That should do the trick, hopefully. And it's accepted, y'all. So let's go ahead and submit it. Make sure it's still accepted after we submit it. And look at that, y'all. 101 milliseconds beats -% of users. Not too bad at all, y'all. So before we go, make sure you get one more look at the code. This is the top part. This is the middle. This is the other part, the bottom of the middle. And this is the rest of the code, y'all. And yeah, y'all, with that being said, I hope y'all learned something today. And I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.